Welcome to the second day of OOPSLA at /Con. It is my great pleasure and honor, I have to say, to welcome now our keynote speaker of today, Joe Hellerstein of UC Berkeley. He is the Jim Gray Professor for Database Systems at UC Berkeley. And his work focuses on data-centered systems, and in this space he covers, I would say, all topics, going from low-level system topics up to programming abstractions. And his work has been recognized by so many awards that I cannot list all of them, but I want to mention, of course, some of them. The ACM Sigmod Code Innovation Award, which is awarded or given for innovative and highly significant contributions of enduring value to the development, understanding, and use of database systems and databases. He's an ACM fellow, he's a Sloan fellow, and he didn't get 1 or 2 Test of Time awards, but 6 of them. The Fortune magazine has included him in the list of 50 smartest people in technology. The MIT Technology Review has included his work on cloud programming to the list of 10 technologies that are very likely to change our world. And he has done also a lot of contributions to the tech industry. He has funded several startups, I know at least of 2. He is a faculty fellow of Sutter Hill Ventures, was director of Intel Research in Berkeley, and technical advisor of several startups, and also established tech companies. Do you want to hear more? I do have at least one item more beyond all those that I mentioned. He is also a pretty good trumpet player, as far as I can judge, as someone that has no idea about, likes music, but does not do music myself. I have been very amazed and following his work for several years at the intersection between databases, database systems, distributed systems, and programming languages, and the talk he will give today, as the title says, basically is also in this space. So without further ado, please join me in welcoming Joe here on stage with a big applause.
Thank you, Laura. You can take that.
Yeah. Oh, you have it, yeah.
Thank you so much, and thank you so much for having me. It's a real honor to have been invited to speak to you. Thanks for getting up and attending. It's my pleasure to be here. So this is joint work, as most of my work is, with just brilliant, wonderful people who I won't have time to really devote to today, because their work is what I'm going to be talking about. Most of these folks are people at Berkeley, with the exception of the people in the gray box who are employed by Sutter Hill Ventures, and my postdoc, May Milano, who's on her way to the faculty at Princeton, but is still at Berkeley. Okay, there's this story we tell in computing, at least in the system side of computing, that with every new architecture comes a programming environment that unlocks the potential of that architecture. And this story kind of goes back to the Ritchie and Thompson Turing Award and the fitness of Unix and C to the mini computer. But you can think about programming libraries and languages and environments that have been developed or accompanied each one of these platforms that allowed developers to build software that was well suited to these platforms. What's interesting is that there's a platform that's as old as the iPhone that really doesn't have its own development environment, and that platform is the cloud. Strangely enough, we're mostly still programming the cloud in sequential languages that were designed long before the advent of widespread distributed programming. And as I'm sure you're all aware, essentially every program you use now is a distributed program. When you're on an airplane, this becomes painfully evident, right? Your Microsoft Word is a distributed program. Everything is in some way interacting with multiple computers these days. And the question is, how can we make it easy for people to program the cloud in ways that, like with the iPhone and the whole idea of there's an app for that, that would allow developers who maybe aren't interested in the platform, they're interested in the applications, to foster the kind of innovation that the designers of the platform never even expected. And of course, the challenge is that distributed programming is very hard. You have to deal with all the issues of parallel programming, as well as the latencies and failures that happen in distributed systems. So then you have consistency issues and partial failure issues and fault tolerance issues. The rise of auto-scaling as a way of making cloud systems cost-efficient only makes this more challenging because the software you write needs to be able to grow and shrink while it's running. It's not like we ship executables anymore. We ship these things that are kind of breathing and living. So it's all very challenging. And frankly, today's compilers and interpreters don't answer the questions that programmers in these environments have to deal with when they have bugs. And so can we do better? I think this is one of the biggest questions in computing, and I've been slowly beavering away at it with my students for quite a while, and it's somewhat embarrassing how long it's taking us to make progress in some ways. I feel very humble about the problem because it's certainly taking my team a very long time to make progress, but we feel like we are slowly but surely making progress. You might ask why a database person like me is even working on this. What do I know about programming languages? Never took a class in programming languages, know very little about them really other than as a fan and a user. But the inspiration really comes from the roots of my own field. So this is Ted Codd, who you may or may not have heard of in your field. He won the Turing Award way back in 1981 for his work in the late 60s defining the relational model of databases. And I think a modern way to think about Codd's innovations were that he was a person who really said that specification should be formal. Think of formal relational languages like the relational calculus, and implementation should be automated by software. And the important thing about this is that implementations can change and adapt over time while the specification remains unchanged. And so when you think about this, he's sort of evolved in some ways. He's passed, of course, but I like to think of the analogy here. Relational databases, as Codd envisioned them, were invented to hide how the data was physically laid out on disk drives, and then how the queries over that data would be executed. And when you think about the vision of what the cloud should be, it was invented to hide how all computing resources are laid out and how all computations are executed. And that flexibility to change the execution is very endemic to this idea of elastic auto-scaling systems. You really want your programs to change while they're running, even though the specification remains the same. All right, so this is why I felt like many years ago that database folks might have something to say in this domain and should get smarter about programming languages and how they're designed and how people use them. So I did some work on programming languages. We have a formal language called Daedalus, which is a distributed data log, which is what we use for much of our formalisms. We had an earlier language called Bloom, which may or may not have wafted past your attention about 10 years ago. The Hydro project is our current project and a much more serious effort. I will say that before we started this project, though, I had students doing systems work. They just wanted to build the kinds of systems that these languages would make possible. And so I'm going to use one of those pieces of work as motivation and as a sort of running example in this talk. And it's a system that's a key value store. So it's a kind of database that just stores, it's like a distributed hash table, if you will. Okay? And for me, this is like the petri dish of distributed systems, or the hello world of distributed systems. But it's a lot richer than hello world. It's got problems in it. So algorithmically, it's trivial. But it forces you to focus on questions of data consistency, questions of performance, and questions of fault tolerance. And there's a wide range of ways you could deploy this to make it elastic, fault tolerant, and so on. And so we had a series of papers that my student Chenggang Wu won a bunch of awards for, actually wonderful work, on this system called Anna. Anna is the name of the world's fastest hummingbird. It's actually the fastest animal on the planet for its size. And it was tracked at UC Berkeley. The ornithologists at Berkeley measured its speed, so that was why we chose the name. So I don't want to go through all these charts. Anna scales linearly, super smoothly across cores and then across machines. So the top chart just shows it scaling linearly. It's extremely fast, even under contention. Many writers trying to write the same key on multiple threads, or if you will, multiple cores, we don't really use threads, And it can be hundreds of times faster than the state of the art. So in this community, perhaps the Intel thread building blocks library is something you're familiar with. We can be 700 times faster than Intel TBB on these highly contended workloads. Other systems were either faster or more cost effective. And with this, we can provide stronger consistency guarantees than many of these systems, and actually pluggable guarantees. You can choose your consistency model by plugging in an appropriate semilattice into ANA, and we'll talk more about this during today's talk. I would like you to focus particularly on the bottom right chart. This is why our performance is so good. In ANA, we spend 90% of our time, even under contention, on what's called good put, on doing actual good work, so on doing puts and gets, whereas all of the other systems we measured spend most of their time just retrying atomics. We didn't do any lock-based systems. They would show a similar behavior. So these systems are spending all their time coordinating and none of their time doing good work under contention. ANA is always putting and getting nearly all the time, which is why it scales so beautifully. ANA was handwritten in C++ by Chen Gang, who's a wonderful developer, and his implementation is correct by assertion, as many such implementations are. It's right because we say so. And you know, that was validating for the design pattern, of course, and we'll talk more about these lattice-based design patterns, but it's not, you know, proper programming languages work, and it's hard to translate across other programs. So the question is, can we make this kind of work easier and more reliable so that anybody can launch things into the cloud very easily? Okay, and with that, I'll give you an overview of kind of what we're doing in Hydro. The long-term goal is to build a language stack, very much an analogy to LLVM. We're very inspired by LLVM, also by Halide, which was the work my colleague Jonathan Reagan-Kelly did. And the idea, of course, is to have optimizations, particularly targeted to our environment, right? But also guarantees for correctness of the code. And the correctness guarantees we want are not the traditional compiler guarantees, they're distributed systems guarantees. I want distributed consistency to be guaranteed, right? Things like that. I want fault tolerance to be guaranteed. So what can a compiler do for me in that environment? And you know, the usual goals you might think of, it should be fast, so particularly interested in low latency because these distributed systems are often interactive services. It should also be flexible. I've tried selling a language. Bloom was an effort to sell a language a decade ago. That was very painful. I don't recommend it. I didn't try very hard, to be frank, but also no one paid attention, so it didn't seem worth trying. Instead, very much in the spirit of LLVM, we want it to be polyglot. We want to have multiple language surfaces on top of our compiler stack using an IR type approach. And then we want it to be cost effective in the cloud. We're now measuring dollars, not just performance these days, yeah? And so we had a vision paper on this some years ago, 2 years ago. Okay, this is the general stack, the envisioned stack for Hydro. So at the top, we want to support many languages. So we're even looking at taking sequential code when we can and trying to turn it into distributed systems, but also distributed programming patterns like futures and actors and functional or logic programming allow many of these languages to bloom, if you will, on top of our framework. And below that, of course, we're going to need some sort of internal representation. So we're tentatively calling this hydrologic. This is a language that does not exist, but it has a very nice name. And the idea of getting from the outer languages into hydrologic is a problem of synthesis in some sense. My colleague Alvin Chung is the person who developed what you may be familiar with as verified lifting, and we're taking some of his techniques and have had some success already in that space. But what we're going to focus on today is the single core IR, okay, so a lower level of the system, which is Hydroflow, which is a quite mature now, I mean, mature, it's about 2 years in, but we're building real things out of Hydroflow. And then under that, this gets deployed in the cloud. So the focus today will be on Hydroflow. It's a Rust-based internal DSL, which of course we then pass to LLVM. LLVM generates a binary. We call such a binary a transducer, which is a word I got from my theory friends, which is you can think of a system that takes inputs from the network and puts outputs onto the network. So it's just a fancy word for a executable that's in a networked environment. Many transducers makes a distributed system. There's no reason in Hydroflow for the transducers to be the same. They can be if you want a single programming multiple data kind of environment, but they can also be heterogeneous transducers talking to each other over a network or over shared memory. Okay, so Hydroflow is an IR and a compiler, and of the folks in the group, these are the folks who've most worked on Hydroflow. Okay, so with that introduction, then let's get into the body of the talk. So it's got about 4 chapters. I'll take you through the IR so you get a sense of it. This is a shared nothing data flow. That's a database systems term. The only thing shared between transducers is a network or some sort of communication channel. So no shared memory, no shared disks. just network communication. All right, so you can set aside all your concerns about shared memory in this talk. There isn't any. Okay. And that allows us to reason in a very nice way. It also allows us to get the kind of performance we saw with the ANA benchmarks. And then we'll talk about how we compile Hydroflow. It's a proc macro-based Rust library and what kind of performance we see. I'll go a bit into the formalisms, which frankly are still work in progress. We were debating them over email on the way here. I decided not to present this as finalized work because clearly it's not, but I'll tell you where our heads are at. And then I'll talk about some of the results, if there's time, a level up from Hydroflow at sort of more the hydrologic level of how we optimize across transducers. Okay, let's begin with the transducer IR then. So it's a graph specification language, and Hydroflow, in essence, is a dataflow programming model. It's a human programmable IR. It's embedded in Rust. So this is very much in the spirit of the IRs for LLVM and Halide. We want an internal language that's really a compiler target. It's mostly, we think, in the future, not going to be programmed by people. But if you're the kind of person who likes to get in and make the system really optimized, it should be in a human readable and writable syntax. Okay, and that's what we'll look at today. Please keep in mind if you don't like the syntax, we don't really expect you to use it in time. I use it, our team uses it, which will write papers, but the hope is that a compiler would be generating this code. Each transducer, as I said, is intended to run on a single core of its own. All right, and this is essentially a typed dataflow graph type of language. And so there'll be statements like this one at the bottom, and you can think of them as dataflow graphs like the one on the right. We can auto-generate these graphs so you can look at your programs visually. We'll see a few examples. And it's not a surprising dataflow language. It's very much like other functional and dataflow languages you've seen before. This is just screenshots from our auto-generated docs from Rust. These are all our operators. I'm not going to walk through them, but you'll see maps and filters and flattens and folds and stuff like that. Okay, so this is pretty familiar. Certainly not my intention to walk you through this. Again, it's a low-level language. Some of these operations are compiler target kind of fusions of multiple operators in one for efficiency, for example. So they're not very interesting, some of them. Let me take you through an example of how to build a key value store using dataflow. It's desperately easy. All right, so this is a picture, sort of an abstract picture of a key value store that runs on a single transducer. Data, rather commands really, come in from the network. You can think of these as put requests or get requests to this hash table, this key value store. We demultiplex them, so the puts go one way, the gets go another way. And really the core of a key value store is just a database join, where whenever there's a get that comes in, we want to look up and see if there are any puts that preceded it that match on key. And that's it. So you can think of this as a streaming join, equi-join, if you will, of gets and puts. The puts get stored in the hash table of the join. The gets flow through and send their output to the requester back over the network. And we'll implement this now in the Hydroflow IR, and it's almost as simple as this picture. So here's the actual Hydroflow IR syntax. We can have a source stream, which we're going to do deserialization on. We're going to demultiplex it into the puts and gets, and this is the way we write this down. And we can assign this subflow a variable name. We'll call it network receive. And then we can keep building on this. So we'll call the outputs of network receive down the put channel, puts, and we'll call the outputs of network receive down the get channel, gets. And those brackets that follow the operator, the put and get bracket, are just the enum types that are in this KVS message with adder enum. Okay? So there's one output for each enumerated type. And then the puts are going to go into the 0th operator of a lookup. The gets are going to go into the 1th operator of a lookup. And then here's the definition of a lookup. It's just an equi-join of the puts and the gets by key. And then the outputs go to the destination. And that's it. That's the program. I'm cheating only a little bit. This is what I'm cheating on. There's a bit of casting, all right, at least in the current syntax, to make sure we understand the types of the messages that are coming in and the types of the messages that we're sending out. This is a working Hydroflow program, what you see on the screen now, that implements a single node key value store. All right, and this is the data flow that's auto-generated by the Hydroflow system to let you sort of look at this thing if you want to see it visually. You'll see the join is the third from the bottom. That demux in the middle is sending the puts and the gets to the two sides of the join. Okay, so how do we make this a replicated distributed key value store? Well, here's the basic idea. We're going to have one more join. And that join is going to hold the names of everybody who's joined the system. So the names of all the transducers, names being, let's say, network addresses, so IP, port. So if you get a peer join command in the demux, one extra kind of message now, we'll put that in a hash table here. And whenever we have to send out a result, a put result, we will do a cross product with that collection of peers, which is to say every put will get sent to every peer. Cross product of puts and peers. Okay? Every put gets sent to every peer. That's simply a Cartesian product or a cross join, if you will. And that's it. And we have to union the messages or multiplex them back onto the network. So that's the change to the program for replication. Now we can run these on many machines for fault tolerance or many threads, right? For fault tolerance as well as for requests capacity scaling, right? Which is the kinds of graphs we were seeing. This is the code that we had to add to the program. I don't expect you to read it. On the left for the replication, it's just getting the peers, storing them in that hash table, and doing the cross join. In the background, there's one more bit, which is that if a peer gets a put, eventually it has to gossip it to everyone through that cross join, and that's what you see at the bottom. The entire data flow for the program is on the right. So it's 2 screens worth of code and one big picture. That's really an implementation of that ANA system that I described. Okay, so there's more power in this IR than I get to show. So we've got a new sort of language above it, just a little bit of a functional syntax that's been implemented by my student Shadaj Ladad, which he built a staged programming library for us to do this, because that's the kind of thing Shadaj likes to do on the weekends. So he's quite a developer. So we actually, as a result, have Hydroflow type syntax that is beautifully integrated into Rust using staged programming. So all of the goodies in your IDE work. So it really feels like you're programming Rust the whole time and you're getting all your type hints. It's a powerful language. It has all the recursion and so on. It supports cyclic graphs as in Datalog, and we allow negation style reasoning using stratification, if you're familiar with that, much like Datalog. So we can do universal quantification. We can do familiar things from functional programming like folds. And these are all operators that you can think of as requiring their entire input before they produce any output, right? A fold, you have to get all the input before you produce the output. And this is very analogous to negation and Datalog, if you're familiar with that. And we can do that. We can actually do it with cycles through negation, which is usually considered not meaningful, but the way we do that is we separate things by time. And this is semantic work that we cleaned up in Daedalus many years ago. So there's one clock, one notion of time on every transducer that marches forward sequentially. And I encourage you to look at the docs if you're curious about the IR further. Okay, let's talk a bit about compilation and performance for this IR. So, you know, I had to live through all the years of MapReduce and whatnot, and the truth is batch processing data flow is really not very hard. Okay, and we do that, but event handling with extremely low latency is much more demanding, and that's what we set out to do when we built Hydroflow. And one of my master's students, now one of my programmers, Mingwei Samuel, is kind of a Rust guy and really thought about this pretty hard, and he has this lovely model of what he calls in-out tree partitioning. So you get a data flow graph, and we're gonna break it into these kind of trees that have ins and out operators, or if you wanna think about it, pull and push operators. And so Hydroflow, remember, it's a Rust crate that generates Rust code from graphs, right? That's the idea of the language, uses proc macros. So what we're gonna do is we're gonna take a graph like this one, we're gonna partition it into ins, which are pull, and outs, which are push. And we're gonna partition this into multiple of these in-out trees. And then we're gonna give it to Rust, and Rust is gonna inline the heck out of it. And it's really, really high performance. So think of this, I'm sorry, I went a little fast. This is a Hydroflow program for graph reachability, classic classic recursive program in Datalog, if you will. And this is how we turn it into an in-out tree. You pull from the left, you push to the right. So you can think of there's a sort of an iterator or a control at the top that's pull, 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 push, 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 pull, push, pull, push, pull, push. And it's trivial to inline this, right? Pull, push is just do the things on the left followed by the things on the right in a single thread. Okay, so you give this graph to the Rust compiler of this pull-push tree or in-out tree, and it inlines everything. And so it's extremely fast. Most of the competing sort of data flow systems, if you think of timely data flow also implemented in Rust, every stage of the operation is a function call. And so we're able to get much better performance than some of the sort of competing libraries on these kinds of programs. So it's really one inline function per in-out tree. Okay. Of course, there's more than one of these in-out trees in a program, and between them we're going to need some buffering, and that's what these sort of handoff operators are. So we're going to stitch a full graph into a cycle, essentially, of in-out trees. All right, this is a reminder of the slide we saw before. The question is, can we match this handwritten C++ in ANA? This was one of our goals 2 years ago when we set out to build a compiler, was to match the performance of ANA, because it was the fastest thing we'd built in my group in this style, and faster than other systems that it was competing with by quite a lot. And so we took essentially the code you saw on the previous 2 slides, and we deployed it on virtual machines that were very like the virtual machines that the ANA paper ran on. So on the left is the original ANA benchmark in C++, 2018. On the right, very similar instances. We're now in GCP, but we picked some sort of modest nodes there to match the performance. And you can see, again, the linear scaling. And the y-axis is about the same. I've tried to make the graphs line up. And so you can see that we're getting about the performance that we got with ANA with this high-level specification, right? So we're starting to see that the raw performance of this compiler can match handwritten code that was really tuned to be very fast. So this is, I was super happy when we started getting these graphs. I felt like it should be doable, and indeed we were able to do it. Let me talk a bit about types and consistency analysis. This is part of the correctness goal of the project. So one of the key challenges in distributed systems is replica consistency, right? We want to ensure that distant agents that are running asynchronously, whether it's across threads or across the globe, agree or will agree on common knowledge. And the classic example is just simple data replication. I'm replicating keys in my key value store, or I'm replicating, cache lines, or I'm replicating memory addresses, yeah? And the classic thing is, how do you know that your different participants agree on some mutable variable x? So in this little illustration, we have this couple, and they agree that x is love, and it's very lovely, but they're separated across the world. They have this shared knowledge, but time passes and things happen, right? And it's quite possible that they come to different conclusions without being able to communicate. So now they're not able to communicate, and unfortunately the person on the left thinks x is now poop, and it's going to cause all kinds of problems, because as they continue to compute with their assumptions, they will come to make very different decisions than perhaps they should. And in systems, sometimes we talk about this as split brain, right? The system now has split brain, and we shall never be able to make sense of it or put it back together. Now, this is all very nice, but it's also very old school in a sense. This is very what I call 20th century computer science. We're worried about reads and writes. Very low level of semantics, like too low level, far too low level. What we really want to do is make sure that our program outcomes are shared across the distributed system. However cleverly we can do that, and maybe we can tolerate reads and writes being inconsistent for a while, as long as we can guarantee that our program will produce the right output. Right? I mean, most of the tricks that are played in systems are of that flavor, but they don't tend to be general to language analysis. They tend to be some sort of, in a special case, if I do this read and that write, it's going to work out. So we want to generalize this in a programming language and a compiler. Now, the classical solution is to just use coordination anytime that a reader and a writer or two writers can conflict. And what essentially we achieve is a global total order of operations, right? Something like linearizability, okay? And this is implemented at various levels of the stack in different ways. So on a processor, you might use atomics or critical sections. In a distributed system, you might revert to distributed protocols like Paxos or two-phase commit. And at every scale of the system, if you make this decision, you fail. It is just go slow. It's the go slow switch for computing, is to do coordination, right? And we saw this with the ANA benchmarks. These, the Intel thread building block library is lock-free, but it's not atomic-free, which means that when you have contention, it just retries and retries and retries and is doing 90% of nothing and 10% of good put. So this is expensive at every scale, and we really want to avoid coordination when we can. That's the game. So the big question is, when should we use coordination, and why should we use coordination, right? At some sort of high level. So when do I need coordination? And it turns out when I was starting to ask this question 10, 12 years ago, there wasn't an answer in the literature. The answers were very unsatisfying. People would say, well, you need coordination to avoid, when multiple parties are contending for a resource. Okay, but really, why do I need coordination? That seems very circumstantial, right? Here's a situation where multiple parties are contending for a resource. You can't be in the same place at the same time. I get it. But there's other solutions to this problem, right? This is a solution to that problem. Yeah, this is the Oakland maze. It allows things that should be in the same place at the same time to not be in the same place, right? By using some clever and very expensive engineering. But it's possible. So I want to ask the question of when do we really need to coordinate, right? Give me a theoretical argument for when we need to coordinate and when we don't, okay? So this is a theory problem, so we got to go to the whiteboard and think about it. Suppose you understand everything about your program semantics. Which programs have some coordination-free implementation where your favorite genius programmer could figure out a way to build it that doesn't use atomics or doesn't use Paxos? And which programs, it doesn't matter how clever your programmer is, there's no way they'll be able to implement it without coordination. And this is a computability question. I give you the language construct of coordination. What can you do with it, and what can you do without it? Right? So what is that green line that separates the coordination-free program statements, declarations, from the stuff in the red that is the rest of the programs? And it turns out there's a very simple answer. So this was a conjecture I had that better theoreticians than I proved, which is that monotonicity is the bright line between things that can be coordination-free and things that cannot. So a distributed program has a consistent coordination-free distributed implementation if and only if it's monotonic. And so we call this the Calm theorem, consistency as logical monotonicity. And there's a series of papers, mostly first authored by a guy named Tom Ameloot, who was a grad student at University of Hasselt in Belgium. And these are beautiful papers, very clever. I tried to explain them in sort of plainer terms to the broader community in CACM a couple years ago. So if you'd like to learn about the Calm theorem, this is a place to start, and then you can go read Tom's papers for the proofs. Now, as a constructive way to stay inside the green circle, a nice way to think is algebraically. And it's much easier to think about for most programmers as well than thinking about logic programming and monotonicity. So we've started to think more in an algebraic frame because it's a lot like functional programming. Frankly, you've got operators, you string them together. It looks a bit like dataflow or functional programming. And the key algebraic construct in this environment, which many of you probably are familiar with, is the notion of a semilattice. So a semilattice is a set and a single operator, all right, and that operator just has to be associative, commutative, and idempotent. Okay? And so, the cool thing about lattices, if you haven't seen them before, is every semilattice corresponds to a partial order. X is less than or equal to y, if and only if x plus y is y, that y absorbs x. All right, and this corresponds to pictures like the one on the right. This is the classic set-subset lattice in what's called a Hasse diagram. So this is just a containment graph of the different points in this lattice. Okay? And because we have partial orders in our algebra, we're compatible, we can get to the top of this lattice, if you will, through many routes. So different nodes can go in different orders or different batches of tuples. Think of associativity as batch independent. I don't care what batch of messages you send me now and what batch you send me in a minute and what batch you send me later, it's associative. Commutativity is order insensitive, right? I don't care what order these things come in. And then idempotence is duplicate insensitive, right? So we can climb this lattice in many different sequential orders, which means different machines can run in different orders with different batching and still get to the same result. All right, so this is the flavor of a thing we want, so it's intuitive that this works. And the connection to monotonicity is that what we're doing is we're going up in the lattice's partial order. This plus operator can only climb the lattice. You never go down again. Okay, and because you never go down again, you'll eventually kind of converge towards the top of the lattice. And we'll talk more about this in just a minute. Right, but this is a way to stay inside the green circle. It's actually not even all of the green circle, it turns out, but it's a happy place where we can construct programs in the green circle, so that's good. And so what we really wanted, as we said, is to get consistent answers from consistent data. So suppose the answer to our program wasn't at the top of our lattice, it was somewhere in the middle, that once we got all the data from everywhere, we were going to land at this point x comma y. Okay. How would we agree that that's the end of the program? How would we agree that that's the answer across our nodes? Again, we could use coordination. We could use an agreement protocol like Paxos so that everybody in the system would say, yes, indeed, I got x, y, and no further. We're done. So that's one way to do it. But it's coordination-full. We don't want to do that. So when is it consistent to read without coordination? Only at the top. So at the very top of your lattice, whatever it may be, this is a very small lattice, but at the very top of your lattice, you can't get any bigger, right? Because you're at the top. And at that point, if you locally know you're at the top, you know everyone else will eventually get to the top. You can send your outputs to the user confident that everyone will agree with you, which is nice. But if it's a very big lattice, like all subsets of a gigantic set, you'll never get to the top. It's ridiculous. Like, how many database queries return the entire database? It's silly, right? And so what we're going to want to do is we're going to want to apply things like monotone functions that take us down to smaller lattices from bigger lattices. And I'll show you how to do this in just a second. But the idea is not to get to the top of some giant lattice, but instead to map ourselves into a nice small lattice that's the output of the program we really want. So here's a program that you really want. It's the program to find a pair of matching socks. Okay, so this is the matching sock lattice. We're going to assume you only have 4 socks. But the cool thing about this, if you know right, is how many socks do you have to pull from the drawer to get a match if there's 2 colors? 3 socks. Very good. All right. So if you think about it, this is the matching sock lattice on 4 socks. And what we want is the true-false lattice, really. Do I have a pair? So I want a function that will take me from the matching sock lattice to the, yes, I've got a matching pair of socks lattice, true or false. What is that function? Well, we can label the things that map to false and the things that map to true. And it's monotone, right? Everything above the green line is true. Everything below the green line is false. And that monotone function has pair. We know it's monotone because you can see, I mean, in the picture, it's obvious that it's monotone. But this is a monotone function from the sock lattice to the Boolean lattice. And that's how we're going to do computing in this coordination-free environment. We're going to need to get to the Boolean lattice via some monotone functions so that we can get to the top of a nice small lattice. It doesn't have to be the Boolean lattice. It could be another finite lattice that you usually end up at the top of. But this is a standard example, is to have what's called a threshold function that gets you into the Boolean lattice. And it must be monotone. If we had a red circle somewhere above that green line, it would be terrible because we wouldn't know if we were done again. We'd get over the green line, and then we'd say, uh-oh, what happens if we get to the red circle? Right? So it has to be monotone. That's what's going to allow us to cast this to the Boolean lattice. Clear? Okay. And so what is Hydroflow going to be? Well, it's going to take lattices and use them in a couple different sort of clever ways. One is that we're going to give you coordination protocols. So first things first, if you want to do coordination, if you have, for example, a program that's not in the green circle, you have a red program, you should be able to implement it in our language. And the only way you'll be able to do that is if you have distributed coordination. So we ship with implementation of Paxos, which I'll mention in a bit. We also have a lattices crate that comes with the Hydroflow implementation. And the lattices we have are composable so that you can build up lattices of lattices of lattices, which is what we did in the Anna paper. So rather than writing clever lattices like the folks who work on CRDTs might do, where a clever PhD student makes up a lattice you've never thought of, we're simply going to compose very simple lattices to create richer structures. So the causal consistency lattice from the Anna paper is up on the right. It's a map lattice of a key and a max integer lattice, nested inside of a pair lattice with a value lattice, that's the values you're storing, nested inside of a map lattice with a key. All right, and I won't go through all this, but these are all very simple lattices that we compose together to get something pretty rich, which is causal consistency. Other things in distributed systems that are classic, so this is kind of a vector clock implementation, but you can get lots of other kind of classic things you want in a distributed system by composing very simple lattices. And in fact, Shadaj, who's the guy who implemented the stage programming, has a lovely paper at last year's OOPSLA about synthesizing these kinds of lattices from sequential code. Right? Because these are correct by construction lattice compositions of very simple lattices, it's great for synthesis. The synthesizer can start putting together all these composite lattices and then checking if they're correct, if they do what you want. All right, so we have this lattice crate. We have a collection of functions or operators that can apply functions like maps and folds, and they can either be monotone functions or non-monotone functions. If they're monotone functions, we can talk about the program continuing to be coordination-free, right? As we saw with the sock example. And then we're going to have some data flow types and properties, which is where we have some work in progress that I want to share with you. So here's a little snippet of Hydroflow as a graph. And the question is, what are the types of the edges? So what is the type of the data coming out of each one of these ports on these operators? And so what we'll say is that everything is a sequence of some order. And the order is sort of happenstance or unknown. So we'll kind of make up or scolomize, if you like that word, a name for each one of these operators. This is the order A. Okay, so this is a sequence of type T with the order named A, and its properties are that the batches of this thing are coming in randomly. So we can't say how this stuff will get associated, right? You might get 3 things this tick and 12 things next tick. We don't know. So it's randomly batched, and it may contain duplicates because it might be coming over a network where there's retries. Right? If you look at the second edge down, though, we've casted this into a lattice L. And so the type is now a sequence of lattice points. Right? Think of the circles in our diagrams before. And this map happens to be a monotone function, so the output of it is still a sequence of lattice points. It's actually still an L in this example, but it might have been in another lattice. And the properties have been inherited. We're still random batch and duplicates. And then there's a fold. So if I tell you that we're going to replicate this program, and on one machine we'll do a fold, and on another machine we'll do a fold, and things are coming in random batches, 5 things here might get folded, and 12 things here might get folded. Very clearly, the answers don't have to be the same, right? There's going to be inconsistency if you have networking upstream of fold. Okay? And that's a sort of easy thing to check through some transitive closures of these types, right? So if you have a random batch input to a non-monotonic operation, you'll get non-deterministic output. And you get a sort of red edge out of there. Okay? So that's the kind of analysis we're going to do to make sure things are all monotone or they're not. And when they're not monotone and they're downstream of networking, you have a problem. All right, so here's another example. All I've changed here is that the source now is local. So this is an iterator, not a network source. So if you look at the topmost box, it's source iter, not source stream. And this has properties none. So it's not random batched. It's the whole batch comes in the first tick. So every machine that runs this program will generate the same iterator with the same outputs. And so you can see that the properties are not random batch. The properties are none. And when we get to this non-monotone fold operator, it's cool. Because everybody's going to run it on the same sequence, the same order of the same data with the same batching. And so it should distribute just fine. So even though we're using a non-monotone fold operator, because it's not downstream of networking, we're good. It's not randomly batched. Okay? Similarly, if we had an operator that wasn't fold, but was something like a lattice merge operator that's associative, commutative, and idempotent, then we can be downstream of the network and we're still good. Because this is batch insensitive, right? We're associative, which means we don't care about batches. So replacing the fold with a lattice merge, we have a program that, again, can be replicated safely without coordination. This is the flavor of analysis we want to do. Okay, and if you look at the Hydroflow graph that comes out of the ANA key value store, there's no red in it. It's all green. And so just at a glance, we can see this is eventually consistent. You can replicate this across machines, and you will get eventually consistent outcomes from this program. Okay, so it's kind of that simple for monotonicity analysis. But it's in the type system and these little meta properties that we're playing with. Okay, I have a little time to talk about the future, if you will, of the project, talk a little bit about optimizations across transducers. So we're going to move up the stack a little to hydrologic. Okay, so think of this as a global programming model now. I'm going to do a specification that's going to run on however many transducers I need. I'm the programmer, I don't have to think about that. Except that hydrologic doesn't exist yet, so we used our old language, which is Daedalus, which is a distributed data log language. Okay, so we're going to imagine that we have a single machine that runs over time, and that's what Daedalus is for. It's a data log with time, essentially. And these kinds of languages can be analyzed for many properties, monotonicity being one of them, so we've just seen monotonicity analysis. But also we have things like functional dependencies from database theory that will let us know which attributes of the data determine which other attributes. So if you think about a hash table, the key determines the value. If you know what key you've got, you know what's in that hash chain. And if we partition our data on the same key across our machines, we can shard our program or partition our program, and it will remain correct in its union of outputs. So we can use this functional dependency theory to co-partition the state across the different machines through the data flow. And you have to work to make sure the partitioning works all the way through the data flow. Another thing we can do with a language like Daedalus is use rich database theory ideas on data provenance to understand how results get generated, why they get generated, and to do rich debugging of bugs, because you can see the full provenance of your outputs. And a theme here is that in distributed systems, the hard part's the data. It's the state and the messages. Things that we traditionally solve in a traditional compiler are not the distributed systems problems. They're problems we're going to solve with LLVM at the bottom of the system, right? But these distributed systems problems are going to be data problems. And so it's perhaps not surprising that using these kind of database type techniques is helpful. So some years ago, my student David Chu wrote a proposal to do an automatic optimizer for fancy distributed protocols like Paxos. Remember, Paxos is a coordination protocol. It is not in the green circle. It is the thing that allows you to be in the red circle. It's very coordination-full. It is coordination. But he claimed that he could use some of our techniques to optimize this. It took him about 3 years. The first paper is now appearing at Sigma in the spring. So it took a while because he had to learn Datalog and Paxos and Rust, all of which are hard. So what are the challenges in optimizing these protocols? Well, of course, the compiler is not going to understand Paxos. There's all kinds of global invariants. I mean, it's very few people understand Paxos, much less compilers. Every time I teach it, I have to reread it. And there's a lot of global invariants that are implicit in these things that aren't really spec'd out. And so how can we prove that if we generate a variant of Paxos, it's correct? If you go to a conference like PodC or even SOSP, you'll find new Paxos or new coordination protocol variants every year, and they're very clever. They're too clever for a compiler to figure out correctness. The equivalence of Paxos outputs to these programs' outputs would be very hard to prove. And indeed, nearly inevitably, there's a paper the next year that says, we found bugs in the protocol. It's just, the literature is like that. It's very tricky, and there's a lot of edge cases. So what we're going to do is something much simpler that should be appealing to compiler folks, which is we're going to do very simple local transformations, where each local transformation is proven to be equivalent from the input to the output. And we're going to do like trivial transformations that come straight out of query optimization for parallel databases. One is to take a program like this component C on the left and break its data flow into 2 different threads that communicate over an asynchronous channel. We call that decoupling. This is like refactoring your program into different subgraphs and having the subgraphs compute over the network. And then the other thing we're going to do is this partitioning I was alluding to before, where you take a component and you hash partition the state and the messages so that each node is responsible for a partition of the messages and the data. Okay? With these 2 simple transformations, we had a paper some years ago. I actually don't have the citation. I think it's VLDB 21. I had a student, Michael Whitaker, who did this by hand. So again, handwritten in Scala, correct by assertion, okay? But he was able to show that he could take simple multi-Paxos, and without any of the fancy stuff that's in all these other papers, just using these basic ideas mostly, he was able to get performance that was about as good as these very complicated, often buggy protocols. The hard part in systematizing this, though, to sort of, we call this auto-Whitaker, because we had to make Michael Whitaker automatic because he got his PhD and left, didn't have him around anymore. And the hard part was, when can you apply these transformations correctly to these data flow programs? So that's what David's been working on and what this first paper is about. And indeed, we get graphs of the sort we were hoping to get. This is a latency by throughput graph, and the way to read these is, when things start to curl backwards, they have saturated. So they're not getting better throughput without sacrificing latency, right? So when these curl backwards, you've sort of saturated. And what you're seeing here is this pink curve here is what Michael was able to achieve in Scala with his compartmentalized Paxos paper. And what you see in blue is just Hydroflow using these rule-based optimizations I showed you in the previous slides. So we took a simple Paxos implementation in Daedalus. We applied these rules systematically to that program, and we got this performance. The yellow curve is sort of just bragging about what Hydroflow can do, because this is actually taking all the tricks from Michael's paper, including ones that can't be achieved with those rules, and rewriting the program to use those tricks. And in that case, what we're just seeing is that Rust and our compiler is faster than Scala. So the yellow curve is the same logic as the pink curve. We get a little bit better throughput latency. But the blue curve is fully automatic optimization in the sense that it's just rewrite transformations. Now, really, David's only halfway there. That is, the rules are proven correct, and they can provide the wins, but it's not automatic yet. He applied those rules by hand. Each time he applied it, it was correct, but he chose which rule to apply where. So what we still need is a cost model for an objective function, for an optimizer. We need to be able to say which of these transformations are better than others, and then a search technique to find the optimal rewritings in this cost space. And this turns out to be very similar to query optimization or to e-graphs, depending on where you grew up. I'm happy to have Max Wilsey joining us at Berkeley, because it turns out that classic query optimization and e-graphs are, if they're not isomorphic, they're damn close. They're really, really close. So we're working this out, but we're using Max's egg library to implement the optimizer for this stuff. Okay, I'm going to wrap up. We have a set of other open questions, which perhaps in the interest of time I will skip because we're nearing the top of the hour. But the design of HydroLogic is one of them. We want to support specs for performance SLOs like cost, latency, and uptime. And there should be facets to this thing, like what consistency level do you really need for which API? And do you want to layer in some kind of security of various kinds? And the Hydroflow Plus language that we're tucking in there may help. this auto-scaling fault tolerance bit of the project is an interesting open set of problems. And then, how do we translate from these libraries down to our IR of hydrologic? And we've got our first results last year at OOPSLA. There's more to be done here. I think some of these will be easy. Like I think actors are pretty much the same as transducers. And futures, I think we can handle very neatly as well. Final thing I'm going to say is that, in this picture, right, the hope is that you program in one paradigm and we translate it to our IR. And this became much more realistic to us with LLMs in the past couple of years. We really now think it would be easy to translate these programs into Hydroflow. I could get ChatGPT to do it. It's just, of course, the question is it correct, right? But I believe this is exactly what declarative specification has come to be, is it's going to be this narrow waist between the generative AI, the green goo of AI, if you will. So this is unformed, kind of messy code generation, and reliable building blocks. And what's needed is a formal language in between, one that we can render to humans so they can eyeball it quickly. This is not a programming language design goal that's been traditional. I want a language that's easy to read. No one's ever going to write it other than a computer, but it's got to be really easy to read. I think that's going to be one of the key challenges in this environment for programming languages. And then, of course, we need to translate it down to formalisms for correctness checking. Right? And declarative specification as this narrow waist between the two is going to be, I think, a very lovely way to do this without overfitting the implementations down below. All right, that's all I prepared for today. Thank you for your attention. And I love to geek out about this stuff. I'll be here all day. So if you're interested in distributed programming, please corner me. I'm here to chat. Thanks.
Thank you very much, Joe, for the very interesting and amazing talk. And I am sure there are questions in the audience.
Yes, in the back.
So, microphone. Okay. It's good to run. Here we go.
Yeah, I was just wondering, this looks a lot like propagator networks. I was wondering if you've ever looked at the research that was done in that field, and if there's, what are the difference that could you learn anything from them? Or
I don't know about that, so I'd love to learn more. Maybe we can talk afterwards.
Absolutely.
Yeah, great.
Okay, so
hi, thanks for the talk. Are there any special, let's say, optimization or affordances that you can make in the case of cloud computing, where you have a better controlled safety and security and failure model, as opposed to general distributed computing?
Interesting. I think where that would tuck in is in trying to meet specs for fault tolerance. So if you told me, you wanted this to be up 99% of the time with this much latency, I would need to reason about such things. Honestly, we're not quite there yet, and it's a little easier for me to think about everything being independent failure, but of course that's not true. So what you're proposing is a very controlled form of correlated failure, I guess you could think, or correlated non-failure. And my hunch is that that's all going to go into some kind of model for quality of service or SLOs, and that's the place where the boring part of machine learning is applied. You learn a model, it works pretty well, you give a guarantee to your customer, and you get so much money, because you really are learning about correlations. But I think perhaps what you're pointing out is we can know something that we don't have to learn there that might make the problem easier, and that seems feasible to me, but we haven't done any work there yet. Yeah. It might be that those are just models you just learn. We'll see.
Hi, thank you for the talk. You had this slide about data flow properties and types. Are you aiming at targeting a specific set of fixed properties like randomness, or are you also aiming to support like application-specific properties like invariants, and then you could maybe check where they get lost in the lattice, for example?
Lovely question. So this is the sort of thing the reason that this is work in progress. I don't have a clean answer to that yet. We haven't even settled on the core properties that we want. We don't want to admit a full sort of SAT-solving kind of problem here till we get what we like, and we're sure that it can be done efficiently. After that, I think it should be sort of, it's the usual transitive property assertions. I don't know that we'll have anything clever to say, but opening the box, it seems to me, then opens us to full verification, which is not something we'd like to do in the core of the system, certainly. But it's very natural. And a very clear analogy to things like taint propagation from security. Yeah. Thank you.
Joe, thanks for the talk. I have a few questions regarding, often when you're building these kind of large-scale distributed systems, the distribution of the data comes into play, right? You have to think about how often will a particular kind of operation happen, and that should control it. If you finally want performance, it has to control how you partition things.
Indeed.
So where in this framework do you see that coming in? Yeah.
Great. So two places. It comes in two forms, and we did this in that second Anna paper by hand. I mean, it was an auto-scaling system, but replication and partitioning. So you want to do replication for proximity, for geo-proximity, so to reduce latency, and of course for fault tolerance. And you want to do partitioning for absolute system scaling, right? So a data item might not be available at every node because that node can't hold everything. And so those are the simple levers that I think allow you to do this. And then again, it's a bit of a performance measurement kind of thing to adjust those levers. And in Anna, what we did was we used the key value store to hold its own metadata. So you would publish performance results into certain keys, and that was a way to propagate information about system performance through the system, and then it would adapt itself by reading those keys and looking and seeing how it was doing. And then one can ask the usual system performance questions of, how do you do with different workloads and so on. And again, this is a workload prediction problem that's probably well suited to simple machine learning models, which is the kind of thing we did in our Anna implementation, but it was very custom. So I think as a toolkit builder, we'd like to make those boring systems papers that are doing little scheduling tricks or little adaptation tricks, that should be libraried out so programmers can train and borrow those models. And I think that's a maturity aspect of the project we're not at yet. Yeah.
Have you done any work on sort of upgrading the dataflow logic transducer by transducer, sort of versioning the actual program itself, and sort of anything you might be able to do there and changes to the program you could do and distribute in a sort of replicated way?
Wonderful. I think there's a couple questions there that I'm not sure I'll successfully unpack on the fly. There's a software versioning question, obviously, and a network protocol versioning question. And then there's a live distributed system kind of rolling migration question in there. And there's a lot of conventional wisdom from people who've been building these systems. And I believe there are tools in the environment that help with that, but we have not yet incorporated them here. And there's at the bottom, I had a thing called Hydrodeploy, which I blithely asserted exists. It's very primitive right now, and I think there's lots of interesting sort of systems work to do there. And I don't have any new ideas there yet, but I think there is quite a lot of work to do there, so it's a great question. Yeah.
Thank you for the very interesting talk. I wanted to ask, you showed this dataflow definition of the ANA KVS or something similar, and that implies that there is a notion of data persistence to your data flow. And I was just curious, how do you know what data to persist between data flows?
Yeah, so in the spirit of this being a low-level IR, it's specified expressly in the operators. So the operators have type parameters for whether they're static, which means the data is persisted across ticks, or not. So folds and joins, all the stateful operators, all of their input ports can be specified as static or tick. And you do this by hand because it changes the semantics of the program. Yeah, so it's part of the specification. I elided that a bit on the screen, but in those joins where I had a can on the left and no can on the right, they were static, comma, tick. Yeah, very good. And of course, data persistence is the whole problem at some level. So that's why I work on this. Over here.
Sophia.
So you whetted our appetite by talking about a specification language, and then you didn't show us anything. I was wondering...
Lovely. I love such a question. That's great.
But please tell us a little bit, and in particular, in this specification language, do you want to say things like this part needs to be sharded? Do you want to say this output can be off by the 10 latest inputs? Do you want to talk about these things?
Wonderful. And those were two very different things. That was a lovely question. So absolutely, I did not show you a formal language, and I'm happy to be called out on that. I would encourage you to read the Daedalus paper, or papers. There's many of them. They have a model theoretic semantics for the language that is, quite nice. And that language is robust. It does not include the things you're describing. So on the one hand, it doesn't talk about implementation at all. It's a data log type language. So it doesn't say anything about sharding, but it admits the possibility that sharding could be there by having a notion of space. So things can have addresses. Your second question was, things like, can we allow this to be missing the last 10 items or something? As a data person, I'm rather skeptical of such things. I think the right specification is probably something about the values in the data, not the number of items. So distributed systems people like to talk about staleness, but they usually mean it only in terms of number of updates. And I'm much more interested in the content of the data. So is it off by epsilon, right? And so that's a question of what's the values that you're updating, how are you changing things? I think it's very interesting to think about this in a kind of probabilistic programming model environment. What could be the possible outcomes of an uncontrolled or a stale program? We're not doing that today. So we're mostly interested in exact consistency so far, or being able to flag that you don't have exact consistency, and then you have to reason about what that might mean for you. So we don't have tools for helping you figure out how inconsistent might you be. Yeah, but the former one about the sharding, I think, is a lower level than Daedalus. It's in the Hydroflow model. Yeah, yeah. Thank you for that lovely question. I appreciate it.
Okay.
Just a quick one. What are the workloads where the system doesn't do well at all?
Great. I think a lot, there's an analogy to, we came at this out of query languages. So, for example, low-level algorithms, implementing quicksort. I challenge you to do it in a language like Datalog. It's quite horrible. It actually, my impression is it can't be done. We ended up building a sort of extra control syntax to get quicksort to come out. You say things like, the thing to my left shall be smaller than me, right? That's what sorting is in Datalog. And it does not lead to quicksort, it leads to bubble sort if you do semi-naive evaluation. So those kind of algorithmics seem to be very poorly suited to these languages. They also are not the kinds of things typically I find distributed systems people worrying about, but I wouldn't promise that we won't run into them. So it's a great question, yeah.
Okay, we are actually 3 minutes above the time, but I will dare to ask the last question myself. Like, any plans, or are you already doing it, kind of automatically finding out where you need coordination? You said that you provide Paxos, for example, implementations as libraries.
Yeah.
But is the developer then supposed to find out where to use them, or any automated reasoning?
Sure, yeah. So that, that sort of green edges in the graph picture with the case where there's a red edge, yes. The red edges are where you need to coordinate if you want consistency. And so right now we're not sticking Paxos in for you, but that's just a macro. And so we're not doing it automatically, but the programmer could easily do it using a macro anywhere they see a red edge. What's a little more challenging is to prove that your implementation of Paxos restores consistency. Can you prove that Paxos is doing its job? Is my implementation of Paxos indeed going to produce the same outcomes in the same order on every node? I would like to do that. I feel like that's doable, but we haven't done it yet.
Thank you very much again. Thank you for being here with us today. Join me in saying thank you.